Hello again, everybody. We're back to look at Chapter 3 for Week 3 of our Introductory Statistics course. Chapter 3, we're looking at describing data numerically. So some of the things we're going to look at measures of center. This will be our first section here. Measures of variation, and then measures of relative standing, sometimes referred to as measures of position. And then box plots, which help us to summarize this data. By the way, variation is often referred to as measures of spread or dispersion. First of all, what does that really mean? Well, when we look at graphing data or displaying data, let's say we want to look at some quiz scores. And let's say we have a quiz where scores range from 4 to 10. So I'm going to make something called a dot plot. And on this dot plot, I'm just going to make a number line numbered from 4 to 10. And then I'm going to look at scores. So let's say I randomly select quizzes, and the first one is a score of 8, so I put a dot above the 8. Next one was a 6, and a 7, and another 7. So there's already a dot over 7, so I stack them up, and I just keep scoring these quizzes and putting the scores on my dot plot. And as my dots move up, I see that they start to form a shape. And so if I take and I draw a line through the top dots, I get a shape something like that. And that, of course, is a bell curve. In statistics, it's called a normal curve. Because in nature, that is the shape that most data will normally take on. So now if I want to describe some distributions, let's take a bell curve, looks something like this. If I wanted to describe that bell curve, one of the things I would say is, well, its center is right about at 5. Or I might have a different one that looks something like this. It's pretty much the same shape, but now this one's center is just a little bit below 7. So that's when I talk about measures of center, that's what we're talking about, is where on the number line is the center of this bell curve. And then I might have one that looks like this. Has the exact same center as the blue curve, only this one's much narrower. Then we talk about variation or spread, that's what we're talking about there, is how wide or narrow is this curve. Now we talk about relative standing or position, we're talking about single data points within this distribution. We're not really describing the whole distribution itself. So it's these first two, center and spread or center and variation, that are describing the shape of that bell curve. So our key concepts here, I'm looking at, when we look at these, measuring the center, there's a couple that are very prominent measures, and there are some others that we're going to look at that are not as important. But it is important to look at those measures of center, mostly the mean and median that we'll look at here, and compare them in order to analyze the data set. So our first measure of center, again, we're looking for the center of that bell curve. We're looking at the mean, or sometimes referred to as the arithmetic mean. This is the number that, well, if we go back to 3rd or 4th grade, it was probably called the average. Now in statistics, we don't call it an average because an average carries other connotations to it that don't apply to the mean. So the mean is where we found we added them all up and divided by how many were there. So it is important, as I said, never use the term average, because even though it's often used for mean, and what we often use to calculate an average is the process of calculating the mean, it can sometimes be used to describe other measures of center, and we don't want to confuse those. So important properties of the mean. The mean uses every value in the population to weight out the center of the population, or the center of the data set. As it uses every data value, which makes it important. Some people feel that makes it very, very important. We'll talk about the use of these different measures of center as we go along here. One thing about the mean that is not good is not very resistant. So what that means is if we have an outlier, which would be either a very small or very large value. If we have a very small value compared to the other numbers in the list, or a very large value compared to the other numbers in the list, it can greatly change the mean. For example, in 1983, University of Virginia advertised that the average mean starting salary of a graduate in their marketing program was over $78,000 a year. Well, that's a lot of money now, but it was a ton of money back in 1983. What they didn't disclose was one of those was their center from their basketball team graduated with a degree in marketing, but was drafted into the NBA, and the NBA was making millions of dollars a year. That changed the data. If you took that one data point out, the mean dropped down to about $23,000 a year. Still good pay for back in 1983, but significantly different than $78,000. So that's what we say, the mean is not resistant. One really small or one really large number like the NBA player could totally change the value of the mean. And that's all resistance is the ability to stay close to the same value even if we do have one of those extreme values or outliers in the data set. So the formula for calculating the mean, as we mentioned, is same as the formula that what we sloppily called an average when we were younger, was just to add up all the values and then divide by how many are there. The notation, first of all, the mean is noted by something called X bar. X with a bar over it, that's the mean. Of course, that is the mean of a sample. If I'm talking about a population mean, we use this Greek letter mu right here. Now in this formula, there's some more notation that we should describe. This symbol here is the summation. All that means in this formula is we're adding up all of the X values. X just stands for each of the individual values. Little n is the number of data points in a sample, and big N is the number of data points in a population. So X bar is just the sum of the data points in the sample divided by the size of the sample. Mu is also a mean, but it's the mean for the population. It's just adding up all the data points in the population and divided by the size of the population. So an example of calculating the mean. So Disney World, I'm looking at wait times to get on popular rides. They came up with this data set. Now, first of all, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. N equals 11 here. This is a sample. That's why I used a small n, because obviously not everybody who waited in line for a ride. They just randomly selected 11 people and took their times. So to find the mean, we add them all up. Gives us a total of 430. And we divide by n equals 11 to get a mean wait time of 39.1. Now, let's say that we had someone was waiting in line for a ride that broke down. And so that wait time ended up being over 2 hours, 135 minutes. If I were to add that into this, of course, I'd be dividing by 12 now because there'd be one more. That would all add up to 565, and I'd be dividing by 12. Well, 565 divided by 12, we get 47.08. 47.1 we'll round it to. That's a significant change from 39.1. We've gone up 8 minutes just because of that one really large data value. So that's a sign of the mean not being very resistant. And 135 really isn't that big compared to the biggest value of 75. It definitely could be much larger than that to be an outlier. Our median is looking at the middle value. If we put them in order that says increasing or decreasing here, I've always done increasing just because it makes more sense to me. It is the value that's exactly in the middle. Another way of putting it is half of the data values are smaller and half of the data values are larger than the median. So the big thing about the median is that it is resistant. As long as we have a decent sized data set, adding one really large or one really small value isn't going to change the median by much at all. However, it does not directly use every data point. So some people view that as a potential weakness of the median. So some of our notation, the abbreviation for the median is X, that little squiggly thing is called a tilde, or sometimes just a capital M. I usually just use a capital M for median. To find the median, we first have to sort the values. You have to put them in order from smallest to largest. And then you need to find the position of the median, and it depends on whether you have an odd number of values or an even number of values to where you find that position. If it's an odd number of values, in other words, little n equals an odd number, it's going to be one of the values in the list. If it's an even number, n equals an even number, then our median is going to be between two of the values in the data set. So here's an example where we have an odd number. So it's the same data set we had before. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. So yes, it's the same numbers, 11 data points in there. The first step would be to put them in order from smallest to largest. So here they've got them put in order. Now they've already circled 35 because 35 is in the middle. Because there's only 11 data points here, it was pretty easy. You could cross off the smallest and largest, 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 and you work your way into the middle to get the 35. But what if it's a bigger data set? If it's 30 or 40 data points, we don't want to be crossing off smallest and largest. So one way to find the position is to take 0.5 or 1/2 times little n. So here n is 11, so 0.5 times 11 is 5.5. 5.5 is a decimal. We round it up to 6. So that's telling us it's the 6th number in our list. 1, 2, 3, 4, 5, 6. That'll be our median. So because this came out to be a 0.5 or a decimal, we knew then that there was an odd number of items in the list. We rounded up to the next number to tell us that that item in that place is the median. If we have an even number of data points in the list, so here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, n equals 12, we'll still put them in order from smallest to largest, but notice there isn't one in the middle. They're saying that the 35 and 45 are in the middle. Again, they're just crossing off the end until they end up with 2 left in the middle. And then they just add them together and divide by 2. They find the mean of those two values, or the center of those two values, to get the median. Again, we could find the position. The position here would be, n times 0.5 or 0.5 times n. N being 12, 0.5 times 12 would be 6. Since this is a whole number, that tells us that there was an even number of data points in this data set. So it tells us our median is going to be between the 6th and 7th number in the list. 1, 2, 3, 4, 5, 6, 7. You can see it's the 6th and 7th number that we use to find the median. So the mode. The mode is the one that occurs the most often, the most highest frequency. Some things with the mode. One very important plus of the mode is we can actually find the mode of qualitative data, because we don't have to sort anything. We don't have to add anything up and divide. We're just looking for the one that occurs the most often. The mode is the one measure of center that we can use with qualitative data. If we're looking for favorite color, we ask what color was chosen the most often, or what color was chosen with the highest frequency. The thing with the mode is the data set can have no mode, or it can have multiple modes. For numerical data sets, really the mode is only useful for large numerical sets. If it's a small numerical set, the chances are that there's not going to be a mode. There's not going to be numbers that are repeated often enough to create a mode. So it's used either for large numerical sets or, again, for qualitative data sets. So finding the mode, we have to be aware that there can be no mode. We can have data sets with no mode. We can have data sets that are bimodal, which means they have two modes. And we have other data sets that are multimodal, whereas they have several modes. Depending on what textbook you're using, statistics has a few different fields of thought on this. Some textbooks will say there's one mode or there's no mode. Others will say you can go up to bimodal. Others have some complex formula where you take the size of the data set and you run it through a formula to figure out how many modes you can have. I mean, if you have a whole data set and all the data points are repeated twice, that's not multimodal. That's no mode, because there's no point that's more often than the others. No data value that's more often than the others. So in this example here, we have these values. If we sort them, it's usually easiest to sort them just like we would for a median. Well, we see we have two 30s, three 35s, and two 50s. Well, 35 is the one that's the most often. That's 3 times. That would be our mode there. If we have two modes, and I kind of disagree with this example, but yeah, 30, 30, 50, 50, and 75. They're saying both 30 and 50 occur twice, so they're the modes. I would say no. 30 and 50 make up all the data points except for one. If there were 8 or 10 data points here and there was two 30s and two 50s and all the other numbers appeared once, then I'd maybe say there's two modes, but I do kind of disagree with this textbook illustration of saying there's two modes in that data set, because there's only one other data point outside of those two values. No mode, well, here there is no data point in this data set that is ever repeated. All the data points appear exactly once, so there's definitely no mode in that data set. Another measure of center that's a little lesser known is the mid-range. And for the mid-range, you just take the largest value, called the maximum or the max, and the smallest value, called the minimum or the min, and you find the mean of those two values. You add those two values together and divide by 2. Again, it's very useful if you sort the data from smallest to largest, like we did with the median, and also, of course, to find the mode. Important values, important properties of the mid-range. The big one is, just like the mean, the mid-range is not very resistant to those extreme values. So some good properties of the mid-range. It's easy to compute because we're only using 2 of the numbers, the smallest and the largest. However, we're not accounting for each of the data points. We're only using 2 of the data points. Sometimes the mid-range is mistaken for the median. It is not. The mid-range will not necessarily be in the middle of the data like the median is. So be careful. Each of these measures of center does describe the center slightly differently. Now, if we have a good data set, the values of the measure of the center should be the same. What do I mean by that? Well, if it's a normally distributed set of data, the mode, of course, will be the highest point of this curve. That's the mode. Well, the mean should be the same value. And the median should also be the same value. And the mid-range will fall in that same value as well. This is a normally distributed set of data. Now, one of the big properties of normally distributed data is it's symmetrical, which means this side is exactly a mirror image of the other side. If it's skewed at all, like this one here is said to be skewed to the left or to the lower end because it's stretched out on the left end. Well, our mode is still going to be the highest point there. The median is going to be pulled slightly off. Remember, the median has to have half the values smaller and half the values larger. But the mode is the one that could be changed the most. The mode could be really slid out over here like that. So if we're analyzing a set of data, the mean, median, mode, mid-range should all be the same number or really close to the same number. If they are, that would tell us that we're approximately normally distributed. If they are not really close to the same number, it tells us we are most likely skewed, and we can actually tell what direction we're skewed by looking at those. I don't know why I wrote mode there, that should be the median there in green. Or the mean in green, I should say. If the mean is significantly smaller than the median in the mode, it's telling us that we're probably skewed to the left. The opposite would be true. If the mean were significantly larger than the median in the mode, we would be skewed to the right. So an example of calculating the mid-range, for this set of data, like I said, it helps to put it in order from smallest to largest. Here we have the largest value is the 75 and the smallest is the 20. We add those two together and divide by 2 to get 47.5 is the mid-range. When we are calculating measures of center, mean, median, mid-range, of course, mode doesn't have to be rounded at all. The mode is one of the data points. It's whatever one occurs most often, so there's nothing to calculate there. Mean, median, and mid-range should be one decimal place past the original set of data. So this set of data here was to the nearest 1. There's no decimals, in other words. So the measure of center is going to be rounded the nearest 10th, 1 decimal place. There's 0 decimal places in the data. We have 1 decimal place in our measure of center. So critical thinking. We can calculate mean, median, and mode for data sets, but sometimes we need to ask, is it a good idea to do that? Does it make sense to calculate with this data, even though it's numbers? So an example here, we're using zip codes. Well, zip codes are numbers, but numerically they don't have a meaning. Their value at least doesn't have a meaning. They're a code to route a mail, but the size of the number doesn't have any numerical correlation to anything that's meaningful. So no, they're just labels. They're not really being used as numbers there. Here we're looking at the ranks of medical schools, ranking them 1 to 10. Well, those are ranks, but if we average those numbers, we're going to get 5 as our average. That doesn't mean anything. The average ranking of those schools is 5. Well, it doesn't matter what order we put them in, the average ranking would be 5. The only time it would make any sense to do, I shouldn't be saying average, the mean ranking would be 5. The only time it would make sense to calculate a mean or a median for rankings is if we had like 7 different organizations ranking these medical schools. And then we could say Stanford had an average ranking of 2.6 out of all these different organizations that rank medical schools. Then it would make sense. But if we're just looking at the one set of rankings, no calculation with those numbers makes any sense. So here we're looking at jerseys of offensive linemen on a professional football team. Again, those jerseys, they denote a position, but they don't have any numerical value as far as the value of the player or the actions of the player. So to calculate with those numbers, again, doesn't have any statistical significance at all. So here we're looking at the compensation of chief executive officers. Really the top 5, the compensation for the top 5 chief executive officers. Well, here you're saying, well, hey, those are numbers we can calculate with them. And that's absolutely true. Those are numbers that we would calculate with. Even though there are numbers we would calculate with, it does not make sense to find a mean or a median of those because it's the top 5. That's not a representative sample of the population. If we say that we randomly selected 10 CEOs out of all the corporations in the United States, that would be different. Now it would be a representative sample of the CEOs of all the corporations. So here, the 50 mean ages computed from the means. Okay, so we're looking at the mean ages of each state in the United States. And let's find the mean of all those means. Well, the mean of means, like this, works only if all of those samples or all those populations are the same size. So if each state had the exact same population, yeah, it would make sense to average together those. That would be the average age of the country. But since some states have way more people than others, New York State has a lot more people than the state of Wisconsin, it doesn't make sense. Because there's a lot more people than the 50 mean for New York should have a lot more weight than the 50 mean for Wisconsin. This is where later on we'll talk about weighted means. And that's what should be used here, is a weighted mean. So I'm going to skip ahead a couple slides just because I disagree with the way they calculate here. I'm going to jump up to the weighted mean here. So the weighted mean is if we have numerical values, but one of them occurs more often, or they occur at different rates, different frequencies than the others, I should say. One example of that is grade point average. Grade point average, your grades in the courses in college don't just get averaged together. You have to look at how many credits that class was. For example, here, this class was an A, but it was a 3-credit class. This class was an A, but it was a 4-credit class. The 3-credit A is saying that basically you get a grade for each credit. So that 3-credit A is really 3 A's. Whereas the A that's 4 credits, that's really 4 A's. And so the weighted mean allows us to account for that. That's really 4 A's. That one should count a little bit stronger than the one that's only 3 credits. And so the way we do that is we weight them. So the way they calculate it out, they show the formula here on this next slide, where the 3 credits times the 4 GPA points for an A, 4 credits times the 4 GPA points for an A. Let's simply look at it like this. I'm going to do a table where I have the grade and the credits. So we have an A for 3 credits, an A for 4 credits, a B for 3 credits, a C for 3 credits, and an F for 1 credit. Well, the A is a GPA of 4. GPA of 4 for that A as well. As B is a GPA of 3. A C is a 2, and an F is a 0. So what we need to do at each step here is we take the grade point times the number of credits. 4 times 3 is 12. 4 times 4 is 16. 3 times 3 is 9. 2 times 3 is 6. And 0 times 1 is 0. So that adds up to 43, I believe. Well, what do we divide that by? Well, we have to divide by the number of credits. Each credit got a GPA. So 3 plus 4 plus 3 plus 3 plus 4 or plus 1 gives us 14. So the average GPA there is 43 total GPA points. divided by 14 credits, which is going to give us 3.071428 approximately. We can keep going with that. So there we have it. That is that weighted mean. That's exactly what they calculated here. They rounded it off, of course, to 3.07. Technically, should be rounded to 3.1 because we only go one digit past what our original data was. All our data was whole numbers, so we can only go to a tenth. And then backing up, I want to talk about calculating the mean of a frequency distribution. The reason I did the weighted mean first is because a frequency distribution is just a weighted mean. In this frequency distribution, first of all, if we have single numbers, this is really easy. If we have a range of numbers like this, we first have to find the class midpoint. We find that by doing 0 plus 14 and dividing by 2 gives us a midpoint of 7. 15 plus 29 is 44, divided by 2 gives us a midpoint of 22. And so we're using that midpoint as our value instead of the range. Next, the frequency here is saying this average value, this midpoint of 7 occurs 6 times. So we had to do that weighting of 6 times 7 gave us 42. And we did that for each of these all the way down. We found the total then here of our frequency times our midpoint. And we found a total frequency here, and then that has to be divided. 1,730 divided by 50 gives us 34.6. Now this is approximate because we were using the class midpoints here. So this class goes from 30 to 44, and 37 is in the middle. We would expect those 14 points, if we were to find the mean of those 14 points, that it would be close to 37 because we'd expect it to kind of average out to be in the middle of that class. But it's very possible that more of those values were closer to the lower end or closer to the upper end, and so that it might not average out. So this is an approximation, so don't ever mistake this for an exact mean. It's always more exact if possible to go back and get all of the individual data points and add them together. Of course, 50 data points is a lot, but it's doable with technology. So now I want to take a peek at Excel and how we would use Excel for each of these calculations. So I'm going to do 2 data sets here, A and B. Data set A is going to be 7, 16, 11, 14, and 12. Notice, I'm going to put it down here, n equals 5. There's 5 data points there. Data set B is going to be 15, 26, 9, 13, 21, and 18. Notice n equals 6 because there's 6 points in that one. To find the mean, the command, and I hate that this is the command because we try to avoid this word in statistics, but the command that Excel uses is average. So we hit equals average. There we get the mean of 12 for those. Equals average here. This will give us a mean of 17 for that data set. Median. Now remember, for a data set with 5 in it, that's odd, so it's going to be one of the data points. So the command is just equals median, and we highlight the data points. Hit enter, and there it is. So equals median. Notice what I'm doing, hitting equals, typing median, then I'm doing the open parentheses, then I highlight the data set. So here we see that for the first data set, the mean and median are both 12. That's telling us that that's probably pretty close to a symmetrical bell curve, normally distributed. For the second data set, oops, I don't know what I did there. Let me back off. For the second data set, we have a mean of 17 and a median of 16.5. A little bit different. The mean is bigger than the median, which is telling us there's a chance that that is skewed to the right. So we'd want to be careful with that. Looking at a frequency table, let's look at a different frequency table. We're going to do the number of classes that you're currently enrolled in. So and then we're going to do frequency here. So let's say we've surveyed students and we found that we have, if they're not in any classes, then we don't consider them a student. So it's going to be 1, 2, 3, 4, 5, or 6 classes. Nobody that we surveyed had more than 6 classes. So we had a frequency of 8 students that had 1 class, 19 that were taking 2, 37 that were taking 3, 44 taking 4, 42 taking 5, and 29 that were taking 6 classes. Now, since this is not a range, we don't have to find a midpoint. We can just use that single value. So here we've got x times the frequency equals 1 times 8. Now we do that for all of these, so that'd be 2 times 19 and all the way down. Now I'm going to find the sum. So I'll drop down here, equals sum, open parentheses, and I highlight that list of numbers. And Excel will give me the sum of that set. The same here, equals sum, open parentheses. I need the total frequency as well to divide. So my mean is going to equal, notice I had equals, I just click on this one, divided by this one, divided by my total frequency, and it gives me 4.005. So basically, 4 classes. On the mean here is 4 classes, is what the mean number of classes that a student is taking. That is everything I wanted to do for this section. We'll do section 3.2 on measures of variation or spread in a little bit.